All right, let's get into it. Along every single coastline on our planet, there are these incredibly powerful, totally unseen forces at play. We're not just talking about tides or the waves you see crashing. Nope, we're talking about something else. Something like invisible rivers that are constantly reshaping our world. You know that feeling, right? You go back to your favorite beach in the winter and you swear it's shrunk. Like half the sand is just gone. Well, you're not going crazy, that's a real thing, and there's a very specific reason why it happens. And the answer is that sand is being literally picked up and moved by these hidden currents. Just imagine these massive conveyor belts made of water hauling millions of tons of sand up and down the coast. They can completely change how a beach looks from one season to the next. So let's start with the big one, the most powerful of these invisible rivers. Now, this one's kind of weird because it doesn't flow out to sea, it actually flows sideways, running right along the beach parallel to the shore. This is what we call the longshore current. So, what is it technically? Well, the official definition from NOAA, that's the National Oceanic and Atmospheric Administration, is pretty straightforward. It's a current that's created by the energy from waves, and it moves water along the coast. But, how does that actually work? It's actually a really neat three-step process. So first, waves almost never come straight into the shore. They usually hit at a bit of an angle. Then, when that wave breaks, its energy kind of splits. Part of it pushes water up the beach, like you'd expect, but a whole lot of that energy gets released sideways, parallel to the shore. And that sideways burst of energy, well, that's what creates this powerful river-like current. And that current becomes the sandy conveyor belt we were talking about. This whole process has a name, longshore drift. And it is, without a doubt, the #1 reason beaches erode and shift over time. This current just churns up sand and carries it down the coast, sometimes for hundreds and hundreds of miles. Okay, so while the longshore current is moving everything sideways, there's another system working at the same time. These are the cross-shore currents, and they're all about that push and pull, the water coming onto the beach and then how it gets pulled back out into the ocean. Now, the most common type you've probably heard of is the undertow. And despite the scary name, it's not some monster that's going to drag you down. It's really just the natural return flow. Think about it. As waves keep pushing water up onto the beach, that water has to go somewhere, right? So it just flows back out to sea underneath the incoming waves, creating this steady, pretty gentle pull along the bottom. But, and this is super important, an undertow is not the same thing as a rip current. A rip current is way more dangerous. It's a fast, narrow jet of water that moves very quickly away from the shore. They're both cross-shore currents, but the rip current is the one you really have to be careful of.
Okay, so for a long, long time, coastal engineers kind of thought they had a pretty good handle on these currents. They had formulas to predict them, more or less. But then, some research uncovered a huge plot twist, a critical detail that everyone had been missing. It turns out, not all waves are created equal. The way a wave breaks changes literally everything.
So there are basically two main types of waves in this story. On one side, you've got spilling waves. These are those gentle, crumbly waves where the foam just kind of spills down the front. Then, on the other side, you've got plunging waves. These are the big, dramatic curling waves that surfers dream about, the ones that crash down with a ton of force. Now, for years, everybody used this one standard equation. It was called the Cirque formula, to predict how much sand the longshore current would move. It was the gold standard. But when some scientists at the University of South Florida decided to put it to the test in a huge lab environment, they found something was very wrong. The formula had a massive blind spot. Okay, just look at this table. This is where it gets nuts. The old formula predicted that both types of waves, spilling and plunging, would move a huge and very similar amount of sand. We're talking over 22,000 cubic meters a year. But the actual measurements from the lab, whoa, they told a completely different story. The real numbers were way, way lower. And more importantly, they were really different from each other. And here is the absolute bombshell. For waves that were basically the same height, the powerful plunging waves moved almost 3 times more sand than the gentle spilling waves. The old formula was completely blind to this. It treated them the same and was just massively overpredicting everything. I mean, the researchers themselves put it perfectly. They said the formula wasn't sensitive to the breaker type, which turned out to be a really important factor. This discovery basically changed the entire game for how we have to think about coastal erosion. So you might be thinking, okay, that's a cool detail from a science lab, but why does it matter in the real world? Well, it matters a ton because understanding these invisible rivers and the waves that power them is absolutely fundamental to how we live along our coasts. This is exactly the kind of research that helps us move from just guessing to actually being precise. When we understand the physics of how different waves move sand, we can build much, much better models to predict how our coastlines are going to change, especially with big storms and rising sea levels. I mean, think of the implications. This knowledge is absolutely essential for managing beach erosion. It's critical for designing things like jetties, so they don't accidentally cut off the sand supply to beaches down the coast. It helps us predict dangerous conditions to keep swimmers safe. It even helps keep shipping channels from filling up with sand. It affects so much. And really, it all comes down to this one big question. The coast is this living, breathing system that's constantly moving, all shaped by these powerful hidden currents. The real challenge isn't to stop them. We can't. It's to understand them well enough so we can work with them. So the question we have to ask is, are we building our communities with the current, or are we stuck fighting a battle we can never really win?